Hi everyone, my name is Mike, and welcome to our YouTube channel. Do you sometimes wonder how the famous Euler's equation, e raised to the power I pi equals -1, where I is the imaginary unit defined as the square root of -1, comes from? Well, you are watching the right video because, in this video, we will look at and prove this equation in detail. The formula e raised to the power I pi equals 1 is a special case of the general Euler's formula e raised to the power I theta equals cosine theta plus I times sine theta, where the input theta is pi. Wait a minute, how is e raised to the power I theta equal to cosine theta plus I times sine theta? Well, let us prove this first, as it will help us a lot in showing that e raised to the power I pi equals 1. To prove that this equation is true, let the right-hand side of these equation be f of theta equals cosine theta plus I times sine theta. Next, we find the first derivative of f of theta. The derivative of f with respect to theta equals negative sine theta plus I times cosine theta. By replacing -1 in the derivative by I squared, since I squared is equal to -1, we get the derivative of f with respect to theta to be I squared times sine theta plus I times cosine theta. Factoring out I, we rewrite the equation. The derivative of f with respect to theta equals I multiplied by cosine theta plus I times sine theta, which equals I times f of theta. This shows a critical property: the derivative of f of theta is proportional to itself, scaled by I. Next, we separate variables and integrate both sides. 1 over f of theta, df equals I times d theta. Integrating both sides gives the integral of 1 over f of theta, df equals I times the integral of d theta. The result of this integration is the natural log of the absolute value of f of theta equals I times theta plus c. Exponentiating both sides removes the logarithm. F of theta equals e raised to the power c times e raised to the power I pi, but remember that f of theta also equal to cosine theta plus I times sine theta. Considering the initial condition f of 0, we see that we get c to be equal to 0. When applying the condition that c equals 0 to our previous equation, we get the general form of Euler's formula e raised to the power I theta equals cosine theta plus I times sine theta, and this confirms that the first equation we wrote is true. From the previous Euler's equation that we just proved, if we put theta to be pi, then we see that e raised to the power I pi equals cosine pi plus I times sine pi, and all this in turn is equal to -1. And all this leads to the famous identity: e raised to the power I pi plus 1 equals 0. This equation elegantly unites some of mathematics' most fundamental constants, e, I, pi, 1, and 0, in a single, profound formula. Thank you for watching. If you enjoyed this breakdown, please like, comment, and subscribe for more engaging math content.